Okay, hi everybody. We are going to be modelling radioactive decay in this video, and as you can see I've got a selection of dice here and there are 20 of them. So we're using each die to represent an unstable atom of a radioactive isotope. So it could be cobalt-60 or strontium-90 or uranium-235. It doesn't matter. But you need to know that each individual die represents an unstable radioactive atom. When we roll the dice, if they land with a 6 uppermost, we're going to say that they have decayed. In other words, their nucleus has fired out some radiation and the atom has changed and become a different element because its nucleus has been altered. When they decay, I'm going to remove them from the sample. So, let's go for a first roll. 20 dice. Now, of course, there is a chance, a random chance, that I could throw 20 sixes on the first go here. The chance of that is very slim, and it is impossible to predict which of the dice might end up with a 6 facing up. Okay, so it's important to understand, like you talked about in maths, I expect, that the roll is random. Okay, so we've got our 20 dice and we've rolled them. I can look round and see that only one has landed with a 6 uppermost. I'm going to take that out of my sample. Okay, let's make this smaller. And now that I've got my sample, I'm going to be able to plot a point on this graph here. So at go 0, there were 20 dice, and after go 1, 1 has decayed, and I'm now down to 19 left. Okay, now we're going to keep going and shaking the dice. So I've now got 19 remaining dice. I'm going to roll all of them, and we're going to do exactly the same thing again. Take out the 6s. Again, weirdly, there's only one 6. Lots of 5s. 1 6. And I'm going to plot that point again on my graph. Go number 2. Should put this point over here a bit. Go number 2 is 18. Let's make that right. Okay. And I'm going to keep going on this. Take out the 6s. 1, 2, 4. Roll 5 6s. We're down to 1, 2, 3, 4, 5, 6, 7, 8. Down to 13 on go number 3. So I'm going to plot that point as well. Go number 3. 15, 14, 15. There it is. Okay. And I'm going to pause now, and I'm going to do a few more, and the next thing you'll see are more points on the graph. Okay, I've done a few more. We're going to keep going. Right, we're on roll number 8. Take another 1 out. Plot the point. I've got none here, so I'm going to keep that the same because time is going on randomly. No dice have landed with a 6. And again, no dice have landed with a 6. 1 6. No 6s. So you can see the chances of decay, or the rate at which I'm rolling 6s, is declining It is still random. And we can keep on going. Now, looking at the shape of the graph now, we're going to attempt to draw a best fit curve through here. Okay, and you can see that a little bit strange at the start here, but if I was going to draw a best fit curve through here, I would take my pen and I would try and steer a smooth curve like this. Very hard to draw on the graph. Okay, and so you can see that although each dice is a random chance of decaying, when we look overall, we get a curved shape to show this decay curve for our dice rolling sixes. Okay, and if we were going to draw it, we would represent this shape like this. Okay, now that shape is really important because it means that although each individual atom has a random chance of decaying, when you've got a large number of atoms, there's going to be a predictable pattern to the rate at which they decay. And that's what this curve represents. So we're going to call this a decay curve. And we've modelled the decay using dice. We've modelled the random nature of decay. And we've shown that even with only a small sample of 20 die, that you still get something approximating to this curved shape. Imagine if you had several billion dice, then you would get a very smooth curve.